Hi, in this video we are going to talk about Euler cycles, so let's get started. What is an Euler cycle? Our goal is to find a cycle in a given graph that visits every edge exactly once, and according to the Euler's theorem, a connected and directed graph is an Euler graph if and only if every node in the graph is of even degree, which means that the number of edges from the given node is even. It can be divided by 2. And there is two main algorithms, the so-called Flory algorithm and the Herholzer algorithm. And Herholzer is a bit more efficient. It has a linear time complexity, so we can decide and we can find the Euler cycle in linear time, which is very, very good. So let me tell a few words about Flory's algorithm. It is a method for finding Euler cycles, and it is not so efficient. And the rules are, you have to pick any vertex to start. From that vertex, pick an edge to traverse. You can't traverse it again, so we marked it as visited. Then we have to travel that edge, and then we have to repeat until all the edges are traversed. There is only one important rule, that never cross a bridge of the reduced graph unless there is no other choice. What is a bridge? That can separate the graph into two subgraphs. So, for example, we have a graph like this with 4 vertices A, B, C, and D. And as I said earlier, we can form an Euler cycle if every node has even number of edges. So A have 2 edges, the B has 4 edges, the C has 2 edges, the D has 4 edges, so all of the vertices has even number of edges, so we can come to the conclusion that an Euler cycle can be formed. So we pick vertex at random, for example C, and because none of the edges is a bridge, we go in the direction whatever we want. We go to D. Then we can go wherever we want, but we, for example, go to B, then we go to A, then we go to D. We just have to check on every iteration that adding the new edge is not going to be a bridge. And in this situation, there are no bridges at all, so we don't have to be very careful. And from B to C, and this is the end of the algorithm. And we can form an Euler cycle, and that's all about the Flory's algorithm. It's not so efficient, so let me tell a few words about the Herholzer algorithm. It is an algorithm to find an Eulerian circuit or Euler cycle in a connected graph in which every vertex has even degree. So we have to maintain 2 stacks, and initially all the edges are unvisited. Choose any vertex V and push it onto a stack. And while the stack is non-empty, look at the top vertex, for example U, on the stack, and if U has an unmarked indecent edge, say to a vertex W, then push W onto the stack and mark the edge UV as visited. And if U has no unmarked indecent edge, then pop U off the stack and print it. The algorithm terminates when the stack will become empty. So we have 2 stacks, the temporary stack and the result stack, and we have a graph containing 6 vertices A, B, C, D, E, and F. We start, first of all, let me check whether we can form an Euler cycle, and we come to the conclusion that all of the vertices has even number of edges. So the degrees are even, so we come to the conclusion that an Euler cycle can be formed and constructed. So we start, for example, at the vertex A, and we just go to whatever we choose. We can go to D, but we, for example, go to B. Then we go to, of course, we have to push the visited vertices to the temporary stack. So the first one was A, then we visited B, and because there are unvisited edges from B, we keep pushing the items to the temporary stack. We have to push the given node, I mean the given vertex, to the result stack from the temporary stack if we get into the situation where all of the edges has already been visited. But in this situation we have 3 edges. For example, we choose C and we push it to the temporary stack. It's very important, not the result stack, the temporary stack. And because there are several unvisited edges in this situation too, we can go to E, F or D. We choose, for example, D and push it to the temporary stack. Then there is only one edge we can visit, so we go back to A and push it to the stack. It's very important that no matter that there is another A in the stack, if we visit it again, we have to push it again. And in this situation, we come to the conclusion that all edges are visited as far as vertex A is concerned. So we have to backtrack, or whatever we call it, I call it backtracking, and go back to D. And yeah, we have to push it to the temporary stack. And as you can see, we push the A to the result stack because we have to push a given vertex to the result stack when we bump into a situation where all the edges have already been visited. And this situation before A has already been visited, so we backtrack, and while backtracking we pop the last item from the temporary stack and push it to the result stack. So that's why A is the first item in the result stack. And the D has 2 edges that already been visited, so we backtracking and put the D, the last item on the temporary stack, to the result stack. So that's, we have 2 items in the result stack. C, we have 2 unvisited edges, so there's no need for backtracking again. We visit, for example, E, and push it to the stack. Then we visit B again, and we push it to the stack no matter that there's another B already in the temporary stack, so we just keep pushing if there is an unvisited edge from the given vertex. And there's an unvisited edge because we can go to F and push it to the stack, and we go back to, there's another unvisited edge, and with the help of this edge we can get to C, so we have to push this C again to the temporary stack. And this situation, we have passed through all the edges, so we have to move elements from the temporary stack to the result stack. So we keep popping the elements from temporary stack and keep pushing them to the result stack. So we put C, then we put F, then we put B, then we put E, then C, then B, then A at last to the result stack. And that's all about this algorithm, because from now on we just have to keep popping the items from the result stack, and that's going to give us the Eulerian cycle. So we just have to keep popping the items from the result stack, as I said earlier, and because A is the first element and then B, then the edge between the A and B will be the first edge in our solution. Then we have to go to C, then to E, to C, then E, then B, then F, then C, then D, and lastly to A, back to the A, because that's the definition of Eulerian cycle, that the starting point is the same as the finishing point. So that's all about this algorithm. It's much more efficient. It is the best known algorithm for solving the Eulerian cycle problem. And for example, in this situation, there's no Eulerian cycle here, because, for example, B has a degree 3 because it has 3 edges. So what can we do here? The solution is that we have to add edges until the Euler's theorem is satisfied. And what is the Euler's theorem? That all of the vertices has even number of edges. So if we put, for example, this edge, and with the help of this edge we can find a solution, so that, for example, like this: A to B, B to C, C to D, D to B, and we can go back from B to D because there's another edge, and then from D to A. So if the Euler's theorem is not satisfied, we have to put another edge or maybe many edges in order to be able to solve this problem. And why is it important? Because this is the solution of the so-called Chinese postman problem, because the Chinese postman problem is the same. We want to go through all edges exactly once. And if there is no Euler cycle, we have to put as much edges in our given graph to be able to find a feasible solution for this problem. For example, here we have to add another edge from D to B, and that solved our problem. So that's all about this video. Thanks for watching.